Okay, let's start off with some of the vocabulary in this section, and namely two terms which will lead to one or two more. The first is inscribed polygons. So we start out with a circle, and of course we'll call it circle O. And an inscribed polygon is a polygon whose vertices all lie on the circle. For example, this pentagon here, ABCDE, is said to be inscribed in circle O. Or you could say that circle O is circumscribed about pentagon ABCDE. Now, another term that admittedly you're not going to hear very often, but we would say that O is the circumcenter, and that is because it is the center of a circle that is circumscribed about a polygon. All right, let's take a look then at circumscribed polygons. And in this situation, a polygon is circumscribed if all of its sides are tangent to the circle. So VW is tangent to the circle, WX is tangent to the circle. We would say that this pentagon is circumscribed about circle O, or we would say that circle O is inscribed in the pentagon. So whichever one is inside is inscribed, and whatever figure, be it a circle or a polygon, is around the outside, that is circumscribed. Okay, O would also be the incenter, since it is the center of a circle inscribed in a polygon. So the incenter or circumcenter always refer to the position of the circle. If it's inscribed, then it's in center. If the circle is circumscribed, then the center is the circumcenter. Okay, let's take a look at the theorems, because they're the kind of theorem that it's easy to forget them, much like the theorems from the last section. The first one is Theorem 93, and it tells us that if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. That would have come in handy in some of the problems in section 10.6. You'll notice that I've highlighted, or I should say I've italicized and bold-faced the word quadrilateral. That's because this theorem deals with any quadrilateral. Doesn't have to be a trapezoid, doesn't have to be a parallelogram, doesn't have to be anything special. Any quadrilateral inscribed in a circle will have angles opposite that are supplementary. Now let's take a look at a proof of that. Let's take a look at A here. We know that angle A will equal 1/2 of arc BCD. Now the opposite angle of angle A is angle C. Angle C will equal 1/2 of BAD. Now if we look at the sum of those two angles, angle A plus angle C, they'll equal the sum or half the sum of those two arcs. But if you notice from the picture, if you added arc BCD and BAD together, they would encompass the whole circle. BCD and BAD make up the whole circle, which is 360 degrees. Half of 360 is 180. So angle A plus angle C is equal to 180, which means they're supplementary. So make sure you get that in their notes. Any quadrilateral inscribed in a circle will have angles that are supplementary. Okay, now there's one other theorem, that's Theorem 94. Let's take a quick look at that one. Theorem 94 is really similar, but you'll notice now I've italicized and bold-faced the word parallelogram, because this is more specific than Theorem 93. It can't just be any kind of a quadrilateral. For Theorem 94 to apply, it has to be a parallelogram. And the theorem says that if a parallelogram is inscribed in a circle, then it's got to be a rectangle. Now let's think about that. If we look at the proof, we know that REXT is a parallelogram, and we're going to prove it's a rectangle. And the way we'll do that is recalling back from Chapter 5 the properties of a parallelogram. You'll recall that opposite angles, like angle R and angle X, are congruent. That's true in all parallelograms. And by the theorem we just learned, we know that since it's a quadrilateral inscribed in the circle, the opposite angles have to be supplementary. So r is congruent to x and r is supplementary to x. Therefore, they must be right angles, since two angles that are sup and congruent must be right. And you'll recall that a parallelogram with a right angle is a rectangle. So that theorem's proven. So let's be clear then. Any quadrilateral in a circle that's inscribed in a circle will have opposite angles that are supplementary, and a parallelogram inscribed in a circle has to be a rectangle. Okay, Ramblers, thanks for watching. Go back and rewatch anything that was troublesome to you, and I'll move on to the tutorials. Thanks for watching. Okay, number 15 on page 490, we're given that a quadrilateral QUAD is inscribed in a circle, and we're given the opposite angles A and Q. Now, since we know that A and Q are opposite angles of a quad inscribed in a circle, they must be supplementary. So x squared plus 100 minus 2x equals 180 degrees. Bringing everything over to the left side and setting it equal to 0, I can now try and factor this. When I do, I see that x can equal 10 or negative 8. Now, normally we're in the habit to cancel out the negative 8, but in this case, you can see that x is being subtracted from 100 in circle Q, and it's being squared for circle A. So this negative root is definitely a viable answer. So we need to plug in both of them in order to get two solutions. And we see that we either get 116 or 80 as our possible answers. Number 16 on page 490 deals with the other important theorem from this section. And it tells us that EFGH is a parallelogram. As soon as we see parallelogram, we have to be thinking that this is going to have right angles in it. It's got to be a rectangle. And rather than draw a radius from O to point J, which really doesn't do us any good, let's try drawing it from O to H and another one from O to F. If we mark the right angle up at G, we can see that we have a right triangle HGF. Since we know that arc HG is 120, I know that angle HFG has got to be 60. So we have a 60, 30, 90 right triangle. It tells us that OJ is 6. Well, that's just any radius. That could be as good as OH. And so I know that OH will represent half the diagonal, so HF is 12. Since that's the side opposite the 90-degree angle, the side opposite the 30-degree angle, which is angle H, is going to equal 6, and the side opposite the 60-degree angle, or HG, will be 6 root 3. So the perimeter is going to be 2 times 6 plus 6 root 3, which will equal 12 plus 12 root 3. Okay, the last problem I want to do for this tutorial is number 20 on page 491. And here they tell us that we have a kite, which is just a quadrilateral, and so we know that the opposite angles will be supplementary. So if angle B is 120, I know that angle D will be 60. And we know that AB is congruent to BC, and that AD is congruent to CD. So if I draw BD, I will have created two congruent triangles, which means that this 120 degree angle is going to be bisected. Since these two triangles are congruent, the 120 degree angle at B is now going to be a 60 degree angle, and the 60 degree angle at D is going to now be a 30 degree angle. That means that angle A has to be a right angle, and we have a 30, 60, 90 triangle. Since we know that the radius of this circle is 3, I can find that BD must be 2 times 3, or 6, which means that AB is 3 and AD is 3 root 3. If we find the perimeter of ABCD, it's just 2 times 3 plus root 3, which of course gives us the answer 6 plus 6 root 3. Okay, hope this helps. Thanks for watching, Ramblers.